And should be going. Good. And let's just do this. There we go. Okay. So we're going to continue. I'm going to review a little bit of where we were last time. And today we're going to actually build a circuit out of quantum gates that can do some of the math that we talked about last time. It'll be, it's a little challenging when you first see it. It took me a while to get my head around it. And then we'll look at a Python program that actually tries to run some of this stuff. So let's have a little review. I want to start with phase kickback, which we saw last time, and kind of the key to building the quantum oracle that Grover needs. And if you remember correctly, this is the version that uses a Toffoli gate, which is sort of like a quantum AND gate in the sense that if both of these control inputs see kind of the logic 1, then this controlled not then essentially flips the logic. So it's kind of like an AND that can optionally flip or not the quantum bit or the qubit coming into its input. So if we look at how this works, we start off with 3 qubits, 0, 1, and 2. By my convention and most people's convention, bit 2 here is the most significant qubit. They start off in this basically logic state 0, which is one of the basis states there. Our little shorthand looks like this. And the NOT gate here turns the 0 into a 1. Again, those are just basis states. Okay, if you remember, 0 just looks like this. It's a 1 and a 0 like that. And a 1 is just a 0 and a 1 like that. Just something like that, if you remember what those look like. Then we have these Hadamard gates. And the purpose of a Hadamard gate is to turn one of the basis states, 0 and 1, into an equal superposition of the two states. The plus version is an equal superposition, basically equal amplitude, where the two components of that complex vector are in phase, have the same phase, and the minus state is an equal superposition of amplitude, but where the two components are out of phase by 180 degrees. And if you remember, negative means 180 degrees out of phase, because that's kind of what negative means according to Euler's formula. So that's kind of the basis there. And if you then remember how the phase kickback worked, looks like this. So we start off by trying to figure out what the input is to this Toffoli gate, and it's this tensor product of the minus and the plus, which yields something that looks like this. All right, again, those are basis states. We've got 3 qubits, so we know we have 2 to the 3rd power, or 8. We have an 8-dimensional complex vector, so those are the 8 basis states written in binary from 0 to 7. And we know that what the Toffoli gate does is it flips those 2 that are marked in red. And if we look at that, we can decompose that into this tensor product here, this minus, and this here, which means that the output state is that, oddly enough, the qubit that's supposed to be controlled ends up being the same as it was and unentangled with the rest. And the ones that are supposed to be the controlling ones, one of the base states ends up being negated. And what we have with those 2 controlled qubits, those controlling qubits, is that they are entangled And we have managed, the Toffoli Gates selects, notice the and here, when both bits are set, it selects that one, because that's the logical and that it's doing. And the effect of all of this is to negate it. This really odd behavior that's called phase kickback. And we looked at that in some detail last time, so I'm just sort of reviewing it here. And the net result of all of this is that in general, we can make this thing called a quantum oracle, where we have any number of qubit inputs and the same number of outputs, and where we've created something that some Boolean function of those qubit inputs that logically inverts this thing here. And if we supply it with just the right input, the output is unchanged, but some special logically selected basis state is negated. And that's called the winner state. And so that's what this quantum oracle can do. And when we looked at Grover's algorithm, we saw that if we start off with all of these n, that's capital N basis states. So for example, if we've got 8 qubits, we've got 256 basis states, and one of them is called the winner. That's the one we're interested in finding. And we learned that we can, using a quantum oracle, negate the amplitude there, or equivalently making it out of phase. And then we learned that if we find the average amplitude and reflect about that average, we can amplify the amplitude of this winning state. And that if we do this, and that amplitude amplification is a unitary operation. We prove that, which means that it can be implemented in a quantum computer. And we've got this important formula here that it's twice this averaging matrix minus the identity matrix. That's the thing that does the trick. That's the thing that's unitary. And we learned that if we applied it the right number of times, which is very approximately proportional to the square root of n, that's Grover's quantum advantage, we can get our answer. So that's kind of where we were last time. And as I said, what we're going to do now is how do we build a circuit that implements all this math? So before we go on, I'm just going to stop and see if there are any questions so far. Okay, hearing nothing, I'm going to move on. So let's think about this amplitude amplification circuit. So first of all, the averaging matrix clearly looks like this. It's all ones, right? So no matter what vector I multiply by this matrix, every row of, if I multiply this by some column vector, every row is just going to be the average of all of the elements. And I can rewrite this as the outer product of a column vector and a row vector. Okay, this is an outer product. And so this matrix here is exactly the same as the outer product of this column vector and this row vector. All right. And I can simplify that using our little notation here. If you remember, this is the bracket notation for a column vector, and this is the bracket notation for a row vector. So I'm just going to simplify this averaging matrix as this outer product written in this way. And in a minute, we're going to see why I'm going to all of this trouble, because what I'm going to have to do here is convert that amplitude amplification matrix, which if you remember is 2a minus the identity, into a set of simple gates like NOT gates and Toffoli gates and whatever that can implement this matrix. So that's kind of the whole goal of sort of quantum programming, is you've got some sort of quantum evolution that you want to do, and you got to break it down into the small pieces that the quantum computer is capable of executing. So let's see what this looks like. So again, what I'm going to be trying to do is make this 2a minus I thing. And I'm going to just rewrite this using what I did before, where this this phi 0 here just represents that column vector or row vector where all of the entries are just 1. Okay, that's what that is. And so I've just rewritten it like this based on the last slide. And I'm going to go through a number of transformations here, and we'll take it one step at a time. So here's the first transformation. And what I want to observe is that this phi 0 here, remember that's a column vector where all of the elements are the same. So that's an equal superposition of all of those basis vectors. And if you remember, the purpose of a Hadamard gate is to turn a single basis vector into an equal superposition. And that's what I've done here. This 0 here, what that notation really means is something that looks like this: 0, 0, 0, n times. Right? That's all. That's the 0 basis state, and that's what that little notation means here. And if I take n Hadamard gates, I can turn that into an equal superposition of all of the basis states, because that's what the Hadamard gate does. And so that's what I've done here. I've taken these equal superposition, this one right here, and expanded it into this product of these Hadamard gates and this much simpler thing. Remember, this basis state is really simple. This basis state looks like this. It's got a 1 and the rest of it are zeros, like that. That's the really simple basis state. That's what this thing is here. All right. And so I've now, let me just erase some of this just to make it clear. So I've just again trying to simplify this thing. And the next step is I'm going to do a little bit of rearranging, which I can do because all of these are matrix multiplies that are associative, and the identity matrix behaves in a certain way that I can take advantage of. The net result being that I can move things around. I can move that 2 inside my parentheses. I can move those Hadamard gates outside. Again, all I'm doing is rearranging things using the property that everything here is associative. And if I go one more step, okay, so now what I'm doing here is what this does here, all right? That's a shorthand for a basis state that's all 1s, like this, okay? That's a shorthand for that. And if I take that basis state and multiply it by, remember, x is the NOT gate. It's the thing that inverts zeros and 1s. So if I have n of these NOT gates and apply it to a basis state that's all 1s, I'm going to get a basis state that's all zeros, because that's what the NOT gate does. All right, so I'm doing a lot of manipulations that may make logical sense, but it's not at all obvious why I'm doing them. In a minute, I'm going to show you why I'm doing all of these things. But again, all I'm doing is some basic manipulations using the fact that these are associative matrix multiplies and using the fact that these basis states are pretty simple. I'm using the Hadamard gate to turn an equal superposition or to turn the simple basis state into an equal superposition. And I'm using the X gates to flip 1s into zeros. So far, that's all I'm doing here, even though it looks kind of hairy. All right. The net result of all this being, I'm going to pull those X's out. And now I've got something here in blue that is going to be fairly simple to implement out of quantum gates. And all I have to do is precede it by Hadamard gates and NOT gates, and also post-process it by the same thing. All right. So that's kind of what's going on here. I'm going to, let's back up again and do this a little bit more slowly. And And this is probably the most challenging part of this whole discussion of turning the math into quantum gates again. So I've taken my averaging matrix and turned it into an outer product of a column vector and a row vector. And I've turned those into a much simpler column vector and row vector, one that has only one element equal to 1 and all the others 0. And I'm using the Hadamard Gates now to turn that into that equal superposition. I do a little bit of rearranging. And then I use the X gates, the NOT gates, to turn 1s into 0s. And then finally, I end up with what I really want, which is I can stick these H's and X's at the beginning and at the end. And in the middle, I've got something which we're going to see in a minute is not hard to implement. All right, so let's take a look at how that's been. Let me just stop for a second. And I don't expect everyone to just immediately grasp exactly what I've done here. I mean, I've introduced a little bit of a new notation that looks like this, just as kind of a shorthand. I don't expect everyone to just look at this and say, of course, this is obviously true, but I want you to see it. I want you to see how this is done. And it's not like, it's not like ordinary computer programming. It's pretty mathematical, but in a minute, we're going to turn this into gates. So let me just stop for a second, see if anybody's got any questions. Maybe that everybody's so overwhelmed by this derivation.
I had a question about.
Yeah, Liz.
Yeah, I had a question about the capital N. And I imagine you get 1 over square root of n in the state vector psi naught. But is that that capital N's got to be related to the little n? And I don't know if this is one step generalized to the size of the phase space, but
yeah, that's
if you want to make a comment.
Capital N is 2 to the little n power.
Okay. Yeah.
Right. So n is the number of bits. Capital N is the number of basis states or the number of components in the quantum state vector or the dimension of the state space if you want. So if n is, 10, little n is 10, then big N is 1024.
Right. And so we're assuming the psi naughts are normalized then by that size.
Yes, exactly. In fact, in the previous slide, you can sort of see the 1 over n there.
Yeah.
And I'm assuming that. I'm sort of ignoring that. Yeah, that's right.
All right, thanks.
Yep. Okay. So this is that thing that was in blue the last time that I now have to see if I can implement in gates. So if you look at this, first of all, the outer product of this matrix, of this column vector and this row vector, remember this column vector here looks like this, all right? This state looks like this. It's a bunch of zeros, and then it ends with a single 1. That's the state. And the same thing, this row vector here is all these zeros, and it ends with a single 1. All right, that's what that is. It's a really simple row and column vectors that is 0 everywhere except it's got a 1 in it. All right, and it's pretty obvious then that the outer product of this column vector and this row vector is 0 everywhere except it's got a single 1 in it. That's it. That's the outer product. So it's a really simple, and again, that's the whole idea. We're trying to really simplify these rotation matrices so that we can actually implement them. And then, of course, this is the identity matrix here. And if we subtract those two, that's what we get. All right. If we subtract those two, remember there's a factor of 2 out here. So if we subtract those two, what we have is something that looks very much like the identity matrix, except that this final element here is negative. So that's this whole expression here. So what can we do with this? You may notice that this big matrix here looks very much like the Z gate that we looked at before. Remember, we had those Pauli gates named after Wolfgang Pauli, and there's an X and a Y and the Z. The X is the NOT gate that we've looked at a lot, and the Z gate looks like this. And you may notice then that this big matrix here that we're interested in, this one here, looks very much like the Z gate. And indeed, what it is, it's a controlled Z gate, right? It's a gate that acts like a Z if all of these other qubits are in the logical one state. So it kind of looks like this, right? It kind of looks like pass this qubit through unchanged unless all of these control lines are logical one, in which case make it a Z gate. So that's what this thing is here, all right? That's what this whole thing that we're trying to do here, this whole thing here, which turns into this, is really just a giant controlled Z gate. All right, if all of the control lines are logical one, then it acts like a Z gate, namely like this. Otherwise, it does nothing. That's what's going on here. And there's an identity, all right, that's easy to show. If you look at these 2x2 matrices that we've looked at before, it's easy to show that a Z gate is equal to the matrix multiply of H times X times H. You can, those are simple 2x2 matrices. You can work that out. It's pretty easy to work out. That's one of the identities. So in the end, then what we've got looks like this. That's our circuit. All right. We've got this controlled NOT gate. It's like a Toffoli gate, except it's got lots of control lines. Instead of just two control lines, it's got lots of them. All right, a lot of them. But in the end, it's just a controlled NOT, or you can think of it as a controlled exclusive OR with these two H gates, one in the front and one in the back. And that implements this formula that we've been interested in, this funny matrix that looks like an identity matrix, but has a -1 on the end. And therefore, if we want to build the complete circuit, then, right, we start with that, and that implements that thing in blue that we saw before. And if you remember, we had to stick a bunch of Hadamard gates and NOT gates on the front and on the end. That's what we had to do. All right, this was the big formula that we made, that we showed was equal to 2a minus I. That is the amplitude amplification circuit. And this is the circuit now. We can make it entirely out of Hadamard gates, NOT gates, and one giant controlled NOT gate that has lots of control inputs and only flips the NOT part if they are all logically true. That's the basic circuit. All right. Now, remember that identity that we had, right? We had an identity that Z equals H X H. Well, we've got HXH right here and right here, right? So we can simplify this a little bit like that. And that's the final circuit, all right, or a circuit. There are other ways of doing this, but this is the one that I was able to work out myself. I think there are, like I said, there are other ways of doing this, but with what I had been able to teach myself, this is the circuit that I worked out. And I know that it's correct because I've run it on IBM's quantum simulator and I get the right answer. Otherwise, with all those mathematical steps, how would you ever know that it's right? But I'm convinced that it is, because when I actually implement this and run it on IBM's equipment, I get the answer that you would expect to get. So in the end, what we've got here is a circuit that does this amplitude amplification. And we're going to turn this now into an implementation of Grover's algorithm. And like I said, we're going to see what it does. All right. So this is kind of what quantum programming is like. There's a bunch of math, and you kind of reduce it to these gates.
Hey, just a question, Bill, about notation.
Yeah.
So we use the symbol X for the NOT operation, but
Correct.
the diagram uses the symbol plus.
Indeed it does, and I'm taking this notation from the sources that I've studied. People when they draw diagrams, they draw the knot with this symbol. And in particular, IBM uses these symbols and these colors in their circuit composers. But people, when they write the NOT gate out as a formula, they use an X because it is the Pauli X gate. Okay, so there's a little bit of inconsistency there, and yeah, this can be confusing at first blush. I'm following the notation that the sources that I've looked at use. Okay, so remember our quantum computer from the first day, right? Where we had, again, my world's most expensive coprocessor, and we have some sort of classical computer doing the control. We're going to set an initial quantum state. We're going to evolve it into a final state, and then we're going to observe it. Now let's see what this picture looks like with Grover. And this is what it looks like. Okay, so basically the same picture, but filled in for Grover. And the initialization looks like this. We start off with everything in quantum state 0. We're going to be creating, we're going to be using a NOT and a Hadamard gate to create this minus state, because we know that if you feed that into your quantum oracle, it can mark the winning state, the one we're looking for, by making it negative. So we need that. And we also know by the phase kickback that we looked at, that the action of the oracle preserves this. It doesn't change, it doesn't get entangled with anything else. And we know that if we take the oracle, which can then negate the state that we're looking at, and run it through an amplitude amplification circuit, and we can do it the right number of times, all right, the net result is going to be that one of the quantum states has amplitude that is very nearly 1.0. The one that we're looking for is going to have an amplitude that is very, very close to 1.0, so that when we observe it, we're going to be observing the state that we want. That's the quantum computer here, all right? That's the idea. And so I'm going to want to say a few things about observation, but that's the machine that we're trying to make that runs Grover. Now, you may ask yourself, gee, what happens, let's say you observe a particular state. How do I know that I've gotten the right answer when the probability isn't exactly 1.0? I mean, there is some finite probability that I'll get the wrong answer. And one simple way of dealing with that, by the way, is if you can make a quantum oracle, you can also make a classical oracle. And once Grover's algorithm has identified a potential correct answer, it's easy to verify that answer with a classical circuit. And if the answer does not verify, you can run Grover again and try again. And that does not really affect the computational complexity of the algorithm, because the classical circuit needs order n tries to find the right answer. Grover needs square root of n, but the classical circuit can verify that answer with a classical version of the oracle in what is roughly a constant time. So that's a way of dealing with the fact that all of these quantum circuits give a non-deterministic observation, right? The final state is not non-deterministic, but the observation is. So let's talk about observation, all right? And this is just, straight quantum mechanics, none of which I remember from college, but which I was exposed to when I was learning this stuff. So here are the rules that has been explained to me by my various textbooks. So you people who are physicists can, correct my impression, but what I've learned is that every observable has associated with it a certain matrix. All right, it's a matrix called Hermitian. Is that how it's pronounced? Something like that. And Hermitian, okay. However that's pronounced. I'll try to avoid pronouncing it so I don't sound like a fool. And it's the idea, it is a matrix that is its complex conjugate, all right? A matrix that is its complex conjugate. And such a matrix has real eigenvalues and orthonormal eigenvectors. And if you don't remember all of your linear algebra, that's okay, because the next slide is going to show a very simple example of all of this. But again, I'm just stating the rules here. And when you observe a quantum system, the observation has the effect of choosing somehow one of these eigenvector-eigenvalue pairs. And that choice has a certain probability. So the probability of choosing a particular eigenvector and eigenvalue in a particular quantum state is the squared length of the projection of this eigenvector onto that state. All right, and again, it's not necessary that you exactly understand this, but these are the rules of quantum observation. And we're going to see how this affects an actual quantum system in the next slide. And the actual effects are pretty intuitive, but I wanted to get the math down here just for completeness. The actual thing that you're going to measure is the eigenvalue. And after that observation, the quantum state becomes or collapses, in some of the terminology that people use, into the eigenvector. So you've got this complex quantum state, and you observe it with somehow with this thing that has this associated matrix that's got all these eigenvectors. And one of those eigenvectors is chosen randomly based upon this probability formula over here. And the measurement that you get is the eigenvalue, and the eigenstate changes, collapses to this thing, to one of the eigenvectors. Measurement is not a unitary operation. All right, it is not a rotation. It is not a unitary operation. It essentially destroys the quantum state, or destroys maybe too strong a word, but it modifies it, and it turns it into just one of a small set of possible eigenvectors. And this is, this is the great mystery of quantum mechanics, as I understand it. Is this, there are all these interpretations of quantum mechanics. Is this thing really collapsing, or are there many different worlds that, I don't know. I'm not going to get into that, but the math is the math, right? And the math works somehow. In fact, it probably works more successfully than any physical theory that's ever been created. So there you go. So we're going to pick a particular Hermitian matrix to make our measurements of a single qubit, and we're going to pick the Z matrix. All right. And this is called the Z measurement basis sometimes. Okay. So like I said, you can measure a qubit any way you want, but by convention on these computers, we use a particular Hermitian, what's called the Z measurement basis. And it looks like this. And it's got two eigenvectors. And the two eigenvectors are just the basis states of a qubit, 0 and 1. All right. 0, that's the 0 state. That's the 1 state. All right. And the eigenvalues are just +1 and -1. That's it. And we're going to call those eigenvalues logical 0 and logical 1, I suppose, if we want. All right. So all of the measurements that are conventionally done on quantum computers are done using this very simple Z measurement basis, where these are the eigenvectors. So after every measurement of a qubit, you're going to get a logical 0 or a logical 1, and the resulting qubit is going to be one of these non-superposition states, one of these simple basis states. So let's take a look at how this actually works in practice. So let's say I've got 3 qubits, all right? 3 qubits, 2 to the 3rd, or 8 basis vectors. You can see them here, 0 through 7, written in binary. Those are my basis vectors here. And let's say I'm in a state where the initial amplitude, the quantum state, has the following amplitudes. So the 0, 0, 1, the one state has amplitude 1 over square root of 3, 0, 1, 0 has 1 over square root of 3, 1, 0, 0 has 1 over square root of 3. The sum of the squares sums to unity, which is what we want. All the other amplitudes are 0. This is a highly entangled state, right? You cannot represent this as any kind of tensor product of individual unentangled qubits. This is a highly entangled state. And I think it's called, it has a name, W state or something like that. You can make them out of gates. But let's say you did this, and let's say I now want to measure qubit 0. All right. So if I'm going to measure qubit 0, all right, the probability that I'm going to measure it as a 0, all right, well, there are only 3 states with non-zero amplitudes, and 2 of them have qubit 0 being a 0, and 1 of them has qubit 0 being a 1. So I've got a 2/3 probability, namely the sum of the squares of this and this. I've got a 2/3 probability of measuring a 0 and a 1/3 probability of measuring a 1. Because if I look at my amplitudes, one of them, this one right here, has qubit 0 as a 1, and the others have it as a 0. All right, so those are my probabilities. If I measure it as a 0, okay, well then that qubit is going to collapse to the 0 state. It is now in the 0 state. And the other 2 entangled states, and so that state is no longer entangled with anything. It is deterministically 0. You can measure it a million times after that, and you will always get a 0 because that's the state that it is now in. But the other 2 bits, the ones that I didn't measure, bit 1 and bit 2, are still entangled, and they now have equal probability 1 over the square root of 2. So that's one possible outcome of measuring qubit 0. If I happen to measure it as a 1, all right, then the other 2 qubits, it can't be that state, it can't be that state. So I already know that the other 2 qubits are in the 0 state. I already know that, and indeed they are. And so if I happen to measure qubit 0 as a 1, all 3 qubits are now in a completely deterministic state, unentangled. So this is really how quantum measurement works. You run this quantum circuit and you start measuring the qubits. And as soon as you measure a qubit, it causes a change in the system with the qubits that are entangled with it. Sometimes leaving them still entangled and sometimes leaving them not. All right. So I've drawn all over my pretty picture. Let me erase some of this so you can actually just see it. But that's what quantum measurement does. And so when I measure my Grover output, I've got a whole bunch of qubits. So I'll start off, I'll measure qubit 0. And since all the output bits are entangled, that measurement, after that bit is no longer going to be entangled. It's going to be a 0 or 1. And the other bits may have changed their amplitude as a result of that. That's what measurement does. Right? That's measurement or observation. And again, I'm measuring in the Z basis state. And really, that's all there is to observation. The math, with the Hermitian and all that stuff and the rules, nice to know. It explains certain things, but the reality of this observation really is best understood in a little table like this, in a little example like this table. All right, any questions about so we've now kind of completed the whole picture of the Grover quantum computer, from initialization to evolution with the Oracle and Amplitude amplification circuits to finally observation. That's the complete picture with the classical control. Okay, any questions so far? Okay, let's talk about, so now that I've got this, I want to test this. I want to see how this works. So the first thing is, I'm going to need a quantum oracle. Like I've already shown the circuit for for the amplitude amplification. I'm going to need an oracle if I'm going to test this. All right. So I said, okay, here's an oracle. Here is a 4 input controlled NOT gate. All right. So here's something where if all 4 inputs are logical 1, then this NOT gate flips. So that's an example of an oracle, and that's going to mark the state where that's going to mark the 1, 1, 1, 1 state. Make it negative. Leave all the other states alone. So that's a simple 4-qubit test oracle that I might want to make. All right. And it marks one particular state. Now, how do I make this? Well, the actual gates that I have to work with, I don't have a 4-input controlled NOT gate, but I do have a TOEFL gate. And you might readily imagine that I've got a 2-input, what is effectively an AND gate. It's pretty easy to wire them together to make a 4-input AND gate, and that's what I'm going to do here. So here's how I'm going to do this. I'm going to say, okay, make me a TOEFL gate here, all right? And I'm going to now add a qubit that is kind of internal to the circuit. It's not really part of the inputs and outputs of the thing, but I need this thing. And this is called an ancillary or ancilla qubit. It's something I need to make the circuit work. And if I then do another AND like this for the other 2 qubits, making myself another ancilla bit, and then finally I AND them together, you can now see that I've taken a bunch of AND gates, a bunch of 2-input AND gates, and turned them into a 4-input AND gate. That's really what I've done here. So it's pretty straightforward logic. I've got my 4 inputs, and I need 3 of these TOEFL gates, 2-input AND gates effectively, to make my 4-input AND gate. And the net result of all of this, as we know, is that this input is going to be unchanged. But one important thing about these gates is that the outputs also want to be unchanged, except for that one state that I'm marking. And in order to do that now, I've got to make sure that these ancilla bits are set back to this logical 0 state. And so here's what I'm going to do here. I'm going to add a TOEFL gate here so that these 2 knots cancel out. And I'm back to my 0 state here. I'm going to add another one there. And now I've got this nice complete circuit here. Let me get rid of this stuff. I've got this nice complete circuit, nice symmetrical circuit that behaves just like I wanted to. These strange ancilla bits that I had to add are preserved. The special phase kickback bit is preserved. And the inputs that I actually want now behave the way I want them to, namely that winning state, the 1, 1, 1, 1 state, is going to be negated. So that's an example of how to make a 4-qubit oracle that can mark this particular state 1, 1, 1, 1. And it's obvious that I can generalize this to any number of qubits that I want. Right? This is for 4. I can generalize this to anything I want. And that's what it kind of looks like. All right. Now, let's say that I wanted to mark a different state. All right. Let's say that I wanted to mark not the state 1, 1, 1, 1, but the state 1, 0, 1, 0. Well, the way to do that is to stick a NOT gate where you want the zeros to be on the input and on the output, like this. And that turns this thing from marking the 1, 1, 1, 1 state into marking 1, 0, 1, 0. So I can mark any state that I want with my little test oracle just by applying these NOT gates. All right. And in normal classical binary logic, this makes perfect sense. You do this all the time. You put knots on the input. The knots on the output are a little bit interesting, and I'm going to show you now exactly why this works. All right, I'm going to show you exactly why this works. Right. So let's say, for example, just for simplicity, I'm going to be working here with 3 qubits instead of 4, just to make the diagram simple. But let's say I've got 3 qubits. So I've got 8 basis states. And I'm not interested in marking the 1, 1, 1, 1 state. I want to mark the 0, 1, 0 state. So what I told you is that I'm going to first put a NOT gate on Q0, which is one of the things that I want to be marked. And what that does then, that NOT gate flips around bit 0. So you can see what's happened here. All of qubit 0, which is the least significant or rightmost bit, they're all just flipped. So that's what's happened. And if I now put a NOT gate on Q2, all right, then bit 2s are all flipped like this. And so the net result of all of this state flipping is that the state that I'm interested in has been shifted down here exactly where my multiple input and controlled NOT gate is going to be doing its marking. All right, so this is how this works. This is why putting those NOT gates in front actually works. It has the effect of shifting this amplitude here down to where it can be affected by those AND gates. That's how that works. All right. So what I want to do now is switch to an actual implementation of this. All right, so let me just stop for a second here. Anybody have any thoughts or questions on what we've seen so far? We've got a circuit that can make a test oracle. I'm not saying this is an oracle anyone would ever want to use, but if I want to test Grover, I need an oracle, and I've got a way of making one that can mark any winning state that I want. And I've got an amplitude amplification circuit. So any questions on that so far before we look at some actual Python code that does this? Okay, so this is the very first Python program I ever wrote. I've never been a Python. People love Python. I've never been a Python programmer. I've programmed dozens of other languages, but Python is the language that you can use to program IBM's quantum computers. So that's the deal here. And so I'm going to show you some Python subroutines. And if you don't know Python, that's okay too. We're not going to get into this in any great detail, but I just want you to give you a sense of what I actually did to program this and get it to run on an IBM machine. And so I've defined this function here called multi-X, which basically makes a multiple input controlled NOT gate. And so what you can do is give it some quantum circuit, QC here. Oops, I'm drawing with my pen, but my pen is not doing it. Never mind. Okay, so there's a quantum circuit, and you give it some number of control lines, however many you want, and some target and some number of ancilla bits. Controls is how many controls you want in this multi-X gate. So all this does, if you remember my circuit that made a 4-input controlled NOT gate from Toffoli gates, that's all this thing does. All right. And so what it does, it says, look, if the number of qubits that I want is greater than 2, if the number of qubits that I want is just 2, right, then all I need is a single Toffoli gate. That does the whole thing. If I don't have any qubits, these are kind of some odd cases here, right? If I've got no qubits, then it's kind of trivial. But the interesting case is here, if I've got more than 2 bits, now I have to take a whole bunch of 2-input Toffoli gates and wire them together. And the basic idea here is you start with this thing called a quantum circuit, which we'll see in a second, and you just add things to it. So for example, if I say qc.Toffoli, what it does is just adds a Toffoli gate to that circuit. And you give it some number of, you give it the control lines that you want. There's control line I and control line, those are the qubit lines I+1, and then the output is here. So the call to create a Toffoli gate is an input, another input, and an output. And again, my inputs are some of the control lines, and my output is one of the ancilla bits. All right. And that's really what I'm doing. All of this code here is basically creating a bunch of, or wiring up a bunch of Toffoli gates, adding them to this circuit. And then, if you remember when we created this thing, after putting in those Toffoli gates, we had to put in a symmetric set of gates to return the ancillas to their 0 state. And that's what this uncompute does. For every Toffoli I add, I'm making myself a list of symmetric gates to essentially what people in the literature call uncomputing, turning the ancillas back into their 0 state. And at the very end, I just add all of these uncompute gates back to the circuit, and I kind of have what I want. All right, so this is my little program here. By the way, I'm writing all of this in Microsoft Visual Studio using Microsoft's Python system with a bunch of libraries imported from IBM. So you can see all those imports here. This Qiskit, Qiskit, that's IBM's quantum library, and there's this thing called a quantum circuit and a quantum register. You can see all those things there. All right, so don't have to understand all the details there, but the basic idea is I have this quantum circuit and I can just add gates to it by saying something like qc.toffoli, and then what are the inputs and outputs. This little subroutine here selects the winning state of an oracle, and all it does is add NOT gates. If it goes through all the bits, there's my winning state, and it goes through all of the bits, all right, and if the bit is set, I just add an X gate, qc.x. That's it. All right, just add an X gate whenever the bit is 0, right? Because that's how I wanted to do that. And then finally, this is the circuit that actually makes a Grover circuit. So I compute the number of iterations that I want from that formula that we had before. That's the number of iterations. I create a brand new quantum circuit here, something like this, number of qubits. All right. And I give it a fancy name, and there's a bunch of things like that. But in any event, I'm creating a new quantum circuit. I'm creating ancilla bits that I need, all this stuff here. And then finally, here's my initialization. All right. So for every qubit in my qubits, I'm going to add a Hadamard gate like that. So everyone gets a Hadamard gate. And then finally, I'm adding the X gate and the Hadamard gate that I need for that bottom qubit that we saw. And then for every iteration of Grover, I add the oracle, and then I add the amplitude amplification to the circuit. And then I add some measurement bits, qc.measure. It's going to be my observation bits. That's my Python code for Grover. That's what I wrote. All right. This is not, IBM actually provides in their library, they provide library routines that implement all of this Grover stuff, but I didn't use them because I kind of wanted to do it myself to make sure I understood it. And to make sure that my idea actually worked. So yeah, if you go to the IBM library, there's just a library routine that runs Grover, but I didn't use it. All right, I wanted to write my own, and I wanted to make it reasonably simple. I mean, it's, what we're talking about is basically, 2 screenfuls worth of Python code. And again, I don't expect you to completely understand all the details here, but basically the idea is you create a quantum circuit and you add gates to it. And let's see what this actually looks like. And by the way, okay, so then I've got some scaffolding here. Again, a bunch of imports. This little thing here says, go out to the cloud and tell IBM what my account number is so I can use their machine. And then I wrote this simulation subroutine or simulation function that actually sends my circuit to IBM's cloud quantum simulator and gets the results back. And then here's the run routine that sends a quantum circuit to either, there's this cool thing here where I can find the least busy quantum computer that IBM's got in the cloud, or if I've got a specific computer that I'm interested in, I can send it to that specific machine. And then finally, I just execute this thing. And in both cases, both the simulation and the running, I'm going to run my quantum circuit 1,000 times because I'm interested in the probabilities here. Okay, so really that's how you use this whole thing. And I'm going to now go to an interactive Python window, again in Visual Studio. And I'm going to say, give me some quantum circuit QC equals Grover. All right, and let's make it something with like 2 qubits. All right, 2 qubits. And the winning state, I'll put this in binary, make it, 1, 0 in binary. All right, so I'm going to make myself call my routine. Okay, so I've got a Grover circuit. 2 qubits, there's only one iteration. The winner is 2. So let's see what this looks like. I can do a qc.draw and tell it not to wrap the line around, something like this. All right, so that's my little circuit. And you can see the H's and the Z's and the X's and all that stuff. You can see these measurement things on the end that it's done here. You can see I've got 2 qubits and 1 ancilla bit. That's what the circuit looks like for 2 qubits. It doesn't look quite as neat as the one that I made in PowerPoint because IBM kind of squishes all these gates together. If I say make something with, say 3 qubits, the winner being maybe 101, something like that. All right, so that's now 2 iterations. And if I draw that, obviously more complicated. And the iterations are just stuck one on top of the other. There's one iteration there, there's the second iteration over here. That's how this thing works. I've now got 3 qubits on the input and 2 ancillas. That's my circuit. So let's say I wanted to run this thing. All right, let's run something a little bit more interesting. I'm going to say QC equals Grover. Let's make it 8 qubits, so 256 states, and we'll make it 0, 1, 0, 1, 0, 1, 0, 1 is going to be my winning state in binary. All right, I've got 12 iterations, 8 qubits. I'm not going to try to draw this, but let's run this on the simulator. So I'm going to say simulate, and I'm going to say simulate my quantum circuit. This is going to be a noise-free simulation, as if I've got a perfect, ideal quantum computer. I hit return, and you'll notice the entire circuit was just sent to the cloud. The simulator ran and returned a result in less than a second. So that's pretty damn good. And what you can see is that this is what the output here is actually a histogram of all of the measurements that were made. And out of 1,000 tries, in this case with a pseudo random number generator, all 1,000 of them return the right answer. All right, there's my answer there. 0, 1, 0, 1, 0, 1, 0, 1. I got 1,000 of those. All right. So that works pretty well. That kind of told me, and I've tried this with all manner of different winning states. I've tried this with all manner of number of qubits. The simulator will handle up to 32 qubits, which is 4 billion basis states. All right, it won't go beyond that. Let's try something else. Let's run this. I'm going to make a simpler Grover here. Okay, one with only 2 qubits. And I'm going to run this on the simulator. And I'm going to add in a noise model. All right, so what this does is it says, simulate this with a noise model. And what it does for the noise model is it goes out on the cloud and it grabs a particular quantum computer that IBM has that has been calibrated and its noisiness has been measured and all of that. And it uses that noise model. This takes a little bit longer, but now what you can see is here, there's the winning state, 1, 0. And it got this winning state 865 times out of 1,000. But it got some of these other states, 0, 0, it got 45 times. 0, 1, it got 36 times out of 1,000. 1, 1, it got 54 times. So you can see that even with just 2 qubits, with a little bit of real world noise, and I'm going to, in a minute, I'm going to talk a lot about what that noise looks like, or maybe some of it I'm going to be doing next time. The winning state still works pretty good. I mean, it still works pretty well, but I've only got like an 87% chance of getting the right answer now with a mere 2 qubits. If I do 3 qubits like this, and I do my simulation like this, now I'm going to have 2 iterations. There we go. So my winning state is what, 101. I get 369 out of 1,000. But it's becoming very difficult to distinguish the winning state from the rest of it. You know, it's pretty clear that even with 3 qubits and real world noise on the kind of quantum computer that I've tried this on, things are kind of falling apart. Now, it's important to understand a couple things here. First of all, this is not a very efficient implementation of Grover. If you remember, I said this is an implementation that I made up so that I could understand it and that I could work with the simple gates that I know about. My implementation uses more gates than are really necessary, okay? So in that sense, it's a less efficient implementation and therefore more noise susceptible. I'm going to be talking a lot about noise in the final session and what real quantum computers can actually do. The other important thing to understand is I don't have access to IBM's state-of-the-art quantum computers. I'm running this, and the noise model that I'm using is an older generation of quantum computer. Okay, and I'm going to be explaining in a moment the different versions that are available, but the ones that are available to me as a member of the public who is accessing the cloud for free it's an older generation machine. And so the newer generation machines will do better. A more optimized circuit will do better. But what we're going to see is that even the best machines available today are going to have trouble running this on, more than a handful of qubits. And I'm going to be getting into that in some detail to explain where the machines are today and what the plan is for building machines that could handle 1,000 qubits. All right, but we're not there yet. All right, so if you're worried about, cryptographic codes being broken, ain't going to happen anytime soon, but I'll explain what the plan is. All right, so this is my experience with this Python program and trying this on the various simulators. Now, I am not going to run this on a real machine today because that takes, when I send this off to a real quantum computer, it ends up in a queue. And on the less busy machines, it takes about a half an hour to get the result back. On the extremely busy machines that I have access to, it could take weeks to get the answer back. So I'm not going to do that, but I have done it, and I'm going to show you now the results that I've gotten. So just give me a second here.
Bill, while you're doing that, I may have just missed something really key here.
Okay.
You've got a Python code and you compute a result. And that's because you're coding the gates, right?
Yes.
But then you have the actual simulated quantum computers So you're really running a simulation of a quantum calculation, but the IBM folks are running a simulation of real physical machines, but it's a different kind of simulation.
Yeah, okay, so I'm not running the simulation at all. The Python code here does not actually, the Python code that I've showed you builds the circuit,
Yeah,
but does not run it.
I see. And then you send the circuit to the
I send the
IBM
circuit to IBM's either IBM simulator, which is a cloud
Okay.
service, or a real machine.
Got it.
When I send it to the simulator, I can ask the simulator to apply a noise model
Yeah.
or not.
Right. I got it now. I understand now. Yeah.
Yep.
Thanks. Yeah.
Yep. So let's take a look at some results here. Okay, again, everybody, I assume everybody can see this. I haven't messed up the video yet. Okay, so here's some Grover parameters that I've tried: 2, 3, 4, 6, and 8 qubits with various winners. Okay, so the number of states that Grover is looking through: 4, 8, 16, 64, 256. Here's the number of iterations. Oops, hang on a minute. Number of iterations from that formula. And then in theory, what is the probability of getting the correct result? So that's what this column here is. In theory, that's my probability of getting the correct result. And where it says 1.0000 or 1.000, that doesn't mean unity. That means rounded off to unity. It's actually probably 0.99997 or something like that, okay? And when I run it on the simulator, I get something that is very close to the theoretical predicted value. That theoretical predicted value comes from those sine waves that I showed you the last time. When I run it on a simulator with noise, all right, I get kind of what you saw before, because I just ran those 2 and 3 qubit states. When I run it on 4 and 6 qubits, the results are indistinguishable from actual noise. In other words, this probability that I get with 4 qubits, 0.056, that's just if it was complete noise. That's as if I'm just throwing darts at a dartboard, okay? So with, and you can see the result on real hardware here. With 2 qubits on a real quantum computer, I got something pretty close to what was simulated. On real hardware with 3 qubits, I got something that's barely above indistinguishable from noise, and I didn't even bother trying it on more than 3 qubits. So you can see the results I got are, you know, pretty pathetic in terms of actually having anything useful. But again, this is not the best quantum circuit, and this is not the best quantum computer. But this is what I actually got. And this is something, you know, like I said, you can, you know, this is something you can actually run on IBM hardware. So we are out of time for it, or approximately out of time. We got 5 more minutes. What I'm going to do next time is we're going to look at real machines. All right. How do you build a quantum computer? We're going to look at trapped ion machines, and we're going to look at superconducting qubits, which are the 2 main competitors right now. We're going to look at their properties. We're going to look at how they behave. We're going to understand why these things are so noisy. And we're going to understand what the plan is in the quantum computing community for making machines that are not noisy, that maybe have 1,000 qubits, which is what you really need to do anything useful. I mean, in order to actually, you know, run Grover to quantum advantage, you know, you're going to need a lot more than 3 qubits. You're going to need 1,000. To actually crack cryptographic codes using Shor's factorization algorithm of any utility, you're going to need 1,000 largely noise-free qubits. So in the final session, what we're going to do is explore real machines, how they work, what their limitations are, and what the plan is for dealing with those limitations. So any final questions? Like I said, I'm going to be posting the recording and the slides. Any final questions for today? Go ahead.
I'm a little confused about the theory versus sim columns and why the the probability drops, but then goes back up?
A great question. That's a great question. So with 2 qubits, so the theoretical values are, remember that sine wave that we looked at the last time? And the idea is to find the peak. Well, the sine wave is not continuous. You've got a discrete number of iterations. And it happened that with 2 qubits, you get lucky. And one of the discrete iterations happens to hit 1.0. And with 3 and 4 and 6 qubits, you don't get lucky. And one of those discrete iterations does not happen to hit that close. But as you get more and more qubits and the resolution of your iterations gets finer and finer, you can get closer and closer to 1.0.
I see.
But that's a great question, because that is counterintuitive looking at this picture. It's just the 2 qubits you get lucky.
Okay,
And after
so with more
one
qubits,
iteration,
you would get even
you're
better.
at 1.0.
Hmm.
Great question.
Okay, thanks.
Other questions? All right, and you may think of questions over the next a week or two. I'm happy to answer emails, but that's where we are now. All right.
Great.
So thanks everyone for joining. I hope this has been
Bill.
comprehensible and amusing.
Both, yeah.
Thank you, Bill.
Thank you,
Okay, you're
Bill.
welcome. All right, take care.
Bye-bye.
Thank you.
Yep.
Bye.